In the previous video, I introduced you to some of the quantities that we use to describe wave propagation. In this video, we're going to derive a relation between some of those quantities. Specifically, we're going to derive a relation between wave speed, wave frequency, and wavelength. First, let's do a quick review of what these quantities mean. The figure over here depicts a situation where someone has thrown a cork into the surface of a calm lake. And as the cork bobs up and down, it produces ripples which propagate along the surface of the lake. Over here, we have an insect sitting on the lake. So as the peaks and troughs of the wave arrive at the position of the insect is going down, up, and so forth. So let's go through a few of those quantities that I introduced you to last time. First, we have the wave speed. The wave speed is the speed at which the peaks and troughs of the wave propagate along the surface. So if this was the actual surface of a lake, you would see these high points on the wave, the peaks, actually moving along the surface of the lake at speed c. We have the period of the wave. To understand the period of the wave, think about the insect here sitting on top of the water surface. As the pattern of peaks and troughs pass through the position of the insect goes up, down, up, down, up, down, up, down. Every time there is a peak at the position of the insect is up. Every time there's a trough at the position of the insect is down. So as the pattern of peaks and troughs pass through the position of the insect is going up, down, like so. The period of the wave is the time interval between one peak arriving at the position of the insect and the next peak arriving at the position of the insect. So if the insect is sitting on top of a wave peak right now, the period would be the time it takes for the next wave peak to arrive. Finally, we have the frequency of the wave. The frequency of the wave is the number of wave peaks per second arriving at a fixed location in the medium. So in this example up here, we might say that the frequency of the wave is the number of peaks per time passing through the position of the insect. I showed you in the previous video that the wave frequency is equal to 1 over the period of the wave. Now let's proceed to deriving a relation between wave speed, wave frequency, and wavelength. So let's say again that we have a wave, a pattern of peaks and troughs propagating along the surface of a lake. And again, let's say that we have an insect sitting here on top of the water so that the insect goes up and down as the pattern of peaks and troughs pass by. So we're going to say that the peaks and troughs in this figure are propagating along at speed c. And let's say again that the distance between two neighboring peaks is the wavelength lambda. We're going to consider a process in which the insect is currently sitting on top of one wave peak, and then we are going to follow along as the next wave peak moves from here over to the position of the insect. So what would be the speed of that wave peak? First of all, we would denote the speed of that wave peak by lowercase c, and that would be equal to the distance that the wave peak travels in some time interval divided by the time interval. With this in mind, let's consider the process where the insect over here is sitting on top of a wave peak, and then the next wave peak is going to start over here and move to the position of the insect. As the wave peak moves from here to here, the distance that it travels would be one wavelength. So I'm going to put in lambda for the distance. Now, the time interval between two successive peaks arriving at the same location is the period. So if the insect is sitting on top of a peak right now, then the time it would take the peak to get there would be one period. Let me put that in here. Now, rewriting this a bit, let me say then that the wave speed is equal to the wavelength multiplied by the reciprocal of one period. But we have seen that the reciprocal of the wave period is the frequency. That gives us that the wave speed is equal to the wavelength times the frequency. So now we have our crucial relation between the wave speed, the wavelength, and the frequency of the wave. Now we're going to do a simple example problem using this formula. In this picture here, I have both a leaf and an insect sitting on the surface of a lake, and a wave is passing through this region that has the leaf and the insect. The leaf and the insect are 2 meters apart, and we're also told that 7 wave peaks pass through the position of the insect every 9 seconds. We would like to find the wave speed. Let's give this a go. Let's start from the equation wave speed equals wavelength times frequency. So if we can get both the wavelength and the frequency, we just multiply those together to get the wave speed. Let's start with the wavelength. Did you notice that in this 2 meter distance between the leaf and the insect, we have 1, 2, 3, 4, 5 wavelengths? Let me mark those in. So here's a wavelength 1, here's a wavelength 2, 3, 4, 5. So 5 wavelengths together make up 2 meters. So we can say that one wavelength would be 2 meters divided by 5, which would be 0.40 meters. As for the frequency would be the number of wave peaks per time arriving at the position of the insect. We are given that 17 wave peaks arrive at the insect in 9 seconds, so we can say that the frequency is 17 divided by 9 seconds. Putting that into my calculator, I get 1.89, and then the unit of frequency is inverse seconds. So now we can get the wave speed. The wave speed would be wavelength times frequency, so let's substitute. Wavelength, 0.40 meters. Frequency, 1.89 inverse seconds. Putting that in my calculator, I get that the wave speed is 0.76 meters per second. So now we have had our first introduction to the relation between wave speed, wavelength, and frequency. This is an absolutely fundamental idea in the study of waves, and we're going to be using this many more times as we continue to study waves in this course. And if in your future lives you enter any sort of a field where wave motion is important, I guarantee you will be seeing this relation far beyond this course.